So good afternoon. So welcome to the afternoon session. And there will be two talks, followed by a discussion session, I guess. And then first talk is, does Rust Spark Joy safe bindings from Rust to Spark apply to the BBQueue library? Will be presented by Cyrille.
Welcome. I hope you all had a good lunch. I present the work of the master student Aïssata Maiga with the great title, Does Rust Spark Joy? What do we need for these two languages combined to spark joy? We want to achieve a safe language binding if we call from Rust code into Spark code, because both languages are very well known to provide a lot of memory safety guarantees. But what happens if we call code in one language from another? So we all know that C and C++ code is responsible for tons of security and safety problems because of memory errors. And how can we call code from one language to another? There is no way then to go through the lowest common denominator. So if we are at the high level of Rust with memory safety, we want to call Spark code, which also has certain provable guarantees and safety. We have to go through this ugly valley of low-level C code bindings, and we lose the memory safety. So the interface through which we do this is called Foreign Function Interface, FFI, and you have to know a lot of conventions and rules to write the code in the right way. So our question was, how can we derive a set of best practices between the two languages, Rust and Spark, which are safe, but the combination is not safe if you're not careful? And so we applied this to a real library and also to a number of small experiments and derived a set of recommendations. It's not yet an automated tool, but maybe in the future it might become one. So memory safety is a big problem, and using this foreign function interface brings it back, even from a safe language. So if we have the start of an execution with memory protection in Rust, we call code in C, we might lose this memory safety, and safety might get corrupted, and then if we go back, we can actually exploit this at the Rust level again, because the assumptions that the Rust compiler and runtime environment make are no longer valid at the level of C, unless you also obey this. So you have to trust the code that you call, but the code that you call also has to adhere to a lot of conventions to keep the safety guarantees from the caller. Now, what are these two languages, Rust and Spark? Maybe you've heard of them. Rust is quite a modern programming languages that has memory safety if we don't use unsafe code at the C level. Spark is a dialect of Ada, which has been around for a long time. And it's very small here, this table. Both languages are amongst the most energy and time efficient languages in the world. Only C and C++ are competitive, and also among the most memory efficient languages. Compare this, for example, to JavaScript, which is very popular, which is like 50 times less efficient in some ways, or at least 5 times more energy hungry. So for embedded software, you still need those languages that maybe students today don't like so much, but they get the job done. And one of the key concepts in Rust and Spark are ownership. Now the image is again very small, but just to show you the key point, when you have a reference, the reference can apply to a whole tree of objects. Now we can have a reference considered to be shared, in which case we can share this with other parts of the program, and they are only allowed to have read-only access. The mutable part of an object, the mutable reference, can only be owned by one function or thread at a time. So if we want to change data, we're only allowed to do this through the owned reference, and any indirect reference is read-only. We can also borrow a reference, we can pass the ownership to someone else, and then our access becomes read-only. And in this way, we have a lot of guarantees when we reason about the program. And if we deviate from this safety, if we call code in C, for example, we must actually be aware how this is implemented. Otherwise, you cannot do this safely. So we must know the invariance of this borrowing mechanism and ownership. Otherwise, the whole assumptions will no longer be valid. The same with Spark. The biggest change in Ada was actually this addition of Rust-style ownership in 2019, so that's quite recent. Ada always had a very strong type system otherwise, so it has a much more fine-grained type system than most programming languages. It also has this, support for certain mathematical proofs that you can ensure that runtime exceptions don't happen. You can't prove that the result it computes is always right, but you can prove in many cases the absence of runtime exceptions. Now, we want to be able to call from Rust to Spark. That's the goal, if you remember. And for this, we want to be able to derive recommendations, at least for the majority of data types. So the first step was to look at what data types are out there. Rust has quite a fair amount of open source code already, especially in the so-called crates library. And we looked at 14 code bases and we found that more than half are numbers, about a quarter are references, then a bit more than 10% are enumerations, and then the rest are other types. So we basically can see that by focusing on the top three, and numbers are primitive types, so that's easier. So by handling references and structs, we can handle a large part of the language, and then arrays are included in others and are of course also important. With Spark, we can in this way cover an even bigger percentage, because structs and references are a bigger percentage, but because there is almost no open source code in Ada, we had a very small code base. So this statistic is perhaps not representative of code in general, because almost no code is open source in Ada. We looked at a number of selected examples first that we designed to just try out different cases of passing data from one language to another. Because there's not so much time, I skipped this. You can read about this in the paper. What I would like to explain you is the main case study, which is the BBQueue library, which is a bipartite buffer, hence the BB in BBQueue. And it implements a queue, but it has a limited size of the buffer. And the idea is that this queue can be used by multiple threads at the same time, and we can read as long as there is data, and we can write as long as there is space. Of course, we could always implement this using locks, but then it would be relatively inefficient. So the challenge here is that we can implement this without locks, but that we use atomic variables in the right way at the right place and still be thread safe. And the way this works is that we have a read and a write pointer in the circular buffer as shown in the top half of the image. So this is the data. We can read from here up to this point until the data is exhausted, and we can write from here until there is no space. And you can see at the bottom half of the image that if we write data, we append this and we wrap around the end of the buffer. And at the same time, we remember how much we've already consumed, so the different limits, they move accordingly. Now the challenges are that we have to implement this correctly by knowing how the buffers are encoded in the first place, and also how this atomic access is managed. Now, how do we implement buffers if we want to be safe? We cannot do this like in C. In C, the buffer doesn't know its size. It's managed by the programmer. And that's why we have so many mistakes, and we always have buffer overruns and security problems. So if you want to do this safely, the language itself has to know the size of the buffer. And therefore, it has to allocate, of course, space for the size, and the layout on the stack or heap are not the same, because we now have a value for the size and a value for the data. So for example, here you can see there is a size information and the number of elements that you can have as a limit. And BBQueue was also chosen because it's the only library that actually exists in both programming languages. So there is an official version in both languages, and then there's one that was adapted to be able to use this foreign function interface. So this was adapted before our work, and therefore it is sort of a realistic case study in that we didn't write our own code and then try to make it work, but we tried to make this work with code that was already written for the function interface for access using C, not between these two languages. And what's also interesting is that the memory block has to be contiguous, so there are many assumptions about this particular data structure, which makes it among the more complex libraries that you can use in an embedded system. So we have this lock-free access, these assumptions about how the memory is allocated. So we think if we can do this one, we can do a lot of other programs as well. Here we can see a bit how the two languages work together. So we have the user of the buffer, which is Rust, and it accesses data through what's called a grant. A grant is a wrapper around read and write access, and internally then it can access the low-level memory. And the memory itself is handled by the Spark implementation. So it implements the atomic variables to handle all the counters for the positions and the memory buffer itself. Now, before we address this big problem, we looked at smaller examples just to see how the different types actually work, because it would have been quite a big step to go straight into BBQueue. So we looked at the different types of parameter handover. For example, there are copy types, there are reference types, and Aïssata studied the documentation and the layout, and then from this derived the exact declaration how this has to be done. So you always have to declare this as a C data type, both in Rust and in Spark, to be able to go through this lowest common denominator and to really specify how the memory is laid out. So you go to Rust, you read how this looks like in Rust, then you design a C struct that has the exact memory layout on the Rust side, so you can pass the argument, and on the Spark side, you again use the same C struct to receive the argument. And then you also have to deal with ownership, etc. So we did this for the different data types, and what's interesting here is that you actually have to give up some of the safety. You cannot use some of the safety features that you normally have in Rust, like ownership. This is because once the data goes out of scope of the first language, the compiler, the assumptions of the compiler are no longer valid, because you can't know what happens when it goes outside of your control, and the assumptions in the runtime environment are no longer valid either. So you want to minimize the amount of code that is handled through this unsafe interface, but you have to let go. You can no longer use the ownership guarantees that people rely on so much normally if they write code only inside the language. So here we can see a simple example just to show how a string looks like. So again, the string has bounds, which it doesn't have in C. In C, it's up to you to know where the string is and how many characters it has. But here, we have two integers to denote the bounds. And then we have the data itself, which is an array of character, a buffer of characters. So that is the same. So we have the C string wrapped in a data structure that mirrors what's in Ada, or the same in Rust too. So in Rust it's similar, except that we have the bounds encoded a bit differently, but it's the same principle. We have information about the size of the string here by the number of elements, and then the low-level string is again a buffer of C characters. Now both of these data structures cannot be exported directly, so we have to what's called forget about it here. So this forgetting means that we let go of all the safety guarantees, and now we have to implement the handover correctly so that the safety guarantees, which are no longer done at the language level, are done at the code level instead. And then we go back to BBQueue. So again, we have to encode the data structure. We also have to handle these grants. We cannot pass them to the other language, so we have to temporarily suspend the safety mechanisms for the data that is passed, or ensure that at the source language, and then the actual change is implemented in the target language, which is Spark. Here we can see how the memory is laid out. So the two sides are not completely up to scale, but again, we have metadata that has to be mapped to correspond to each other. So it's a copy of the metadata, but it has to have the same size limitations. And then a pointer to the buffer, which is shared. And atomicity has to be ensured, and the right memory layout has to be ensured. So these are maybe the most important part about these good foreign function interface FFI design principles. So the layout and behavior of the code have to be ensured by writing the code in the right way, because the runtime environment no longer guarantees it. And figuring this out was the task of the student. So there's unfortunately not so good documentation about how to do this step by step. Instead, you have to look at the documentation of the language itself and derive this. So there was a gap in how far this description goes. It basically ends at the foreign function interface level, but it doesn't really carry you through all the way. You can also not use high-level references, because those have the ownership principle, so you have to go back to low-level pointer, and a small mistake can break the memory safety. So we used a memory checking tool, Valgrind, to ensure that the code is actually still correct, at least as far as the test cases go. Here we can also see how this is done for different data types. So we cannot use strings that can be borrowed and that exist only once physically, but we have to go to these low-level strings where ownership is hidden by the user and memory is managed by the programmer. Certain parts of the memory are also not straightforward to access, and certain concepts are not exactly the same between Rust and Spark. So, for example, the ownership is a bit less powerful and flexible, but the memory allocation is a bit more powerful in Spark. So again, you have to kind of find the lowest common denominator and try to express everything as C code. Furthermore, both languages have exceptions, which are a great way to manage error states. Unfortunately, you cannot use exceptions across the language boundary. So this would violate these good citizen behaviors for the foreign function interface. The reason is that Spark doesn't directly use exceptions, and the state at which you would end up when propagating exceptions through the language boundary is not defined. So we would have unexpected changes in the state of the inner language, and they would then not propagate correctly back up to the outer language, at least not unless the runtime interfaces and runtime environments are changed, because we go through C at some point where we have no exceptions, and the exceptions would also not be implemented in the same way. I mean, Spark is basically an error code. So we have to make sure that we don't throw exceptions at the lower language. So our conclusion is it's feasible to write memory safe code when calling from Rust to Spark. The student also thinks it's feasible to create an automated tool, but that would be probably several years of effort. But the documentation really doesn't help you. So it took a few months to figure out all the details. We did this by examples, and you can see the examples in the paper. There are about 8 or 9 representative cases for different types of arguments and usages which we implemented in each language. And if you follow the way that the languages work at the C interface layer, you can preserve consistency. But then if there is an error or exception, then you're again faced with additional challenges. So it's very easy to fool the compiler and make this unsafe, but our goal was, of course, to make it safe. So we did our best, and we used the memory safety checking tool to ensure that none of the tests reported any memory safety violations. And I think early in the work there were 1 or 2, and then Aïssata fixed the bugs, so now the code all passes these safety checks. This is all done through the C interface and the application binary interface in C, so that's why it's called ABI there. And you also have to use the right compiler flags to avoid any optimization that might, again, break the safety. So, for example, you can't have name mangling. You have to use this C representation internally, that there is no change in the memory layout, and certain other features in each language have to be used so that the code really comes out the way you expect it to come out, so that the compiler doesn't make any improvements that would then break things again. Thank you for your attention, and please ask if you have any questions. I'm trying the best I can. So unfortunately, Aïssata is not here who could answer all the questions, but I'll try.
Any questions? Does this work? Yes. You mentioned that it's not possible to move ownership from Rust to Spark. And like the way I understand this FFI, like it's not possible because the FFI doesn't allow you to write like &mut something into the specification of the external function, right? But doesn't this still mean that you could like logically move ownership around and just like convert the pointer unsafely to a raw pointer and then on the other side convert it back?
Yes, that's what we kind of do. So it's also that we only call code in Spark from Rust, and there is currently no callback or going the other direction. So this helps a bit. Some of the reasons why we can't just pass ownership is that in Rust you can also use array slices, so subsets of an array, because Rust thinks it owns everything. So if you were to pass an array slice to Spark, then Rust would think it owns the rest, but on Spark you can only get the whole array. So this is one example how the assumptions could easily break, because the languages are not exactly the same. And originally we were hoping to do both directions, but it was actually challenging enough to do one, and then the other direction is left to future work. So maybe the student will someday do a PhD thesis, then we could do the opposite direction, but this is still open.
Yeah. Could you use this as a basis for a wrapper Spark in Rust? I mean, you rely on the wrapper C macro in the end, right? To use the C ABI and say, oh, it must be exactly this bit representation as in C. But could you argue now, given this experience, that there should be a wrapper Spark in Rust to be closer to what you need?
Yes, except that there are certain cases which we haven't covered, which we didn't need for the BBQueue library, but most of them we did cover. And it is similar to this morning. It is a procedure that you can follow to get the wrapper, but it's not yet the tool that generates the wrapper. So like with the railway, creating a tool that would actually do this for all the cases with automation, that would still take significant effort.
Any more questions?
So I have some probably simple question. So I guess there's some big motivation to connect Spark and Rust. There should be. So then could you slightly explain a bit of a potential reason why Spark and Rust be combined? So actually, I may probably need some more background.
Yes, so it's not only this that they are the most efficient languages. They also combine a lot of paradigms that are popular. So they're both object-oriented and therefore also imperative, and Rust is also functional. I think a big reason is that Ada has been very established in the embedded systems community for many decades, especially for software that is safety critical. So for example, one of the co-authors is from Ferrous Systems, so that's a company producing railway signaling systems. The other one, co-author, is from AdaCore, where they work on the language. Then Rust has really had quite a fast growth in usage since it was invented and released. So I think it's less than 10 years old, but there is currently an effort to write all the GNU core utils in Rust. So all the shell function, for example, ls, rm, etc., all these shell tools are currently being rewritten in Rust, including the C library functions that they rely on. So this is going to provide a very large code base of code that is guaranteed to be memory safe, which you can use. So there is really a big incentive to take advantage of this, because this code is also re-engineered to some extent to be a bit more elegant than the old implementations of the C code that go back about 50 years in some cases. So because of better software engineering practices, Rust has the potential to become a better C library in the next 5 years. So we really want to know how we can take advantage of this for building safety-critical embedded systems.
It's basically then, is the Ada side, Spark side, to use Rust memory safety feature somehow?
Yes, that's in the future, I think, going to be a big direction. But also, there are certain things in Spark that are not in Rust, so that was the immediate motivation here. But I think in the long term, the opposite direction might be more important, because there's so much Rust code out there as open source code that you can reuse. And most of Ada code is proprietary and you cannot access it. So we don't really know globally what the usage patterns and data types are at scale.
Okay, thank you so much. So I said now it's a time, so...
I think you. Do we have more questions?
We have one, but we can clarify this offline.
Okay, or we have some discussion time also after the next talk.
Okay, thanks for the speaker.
Thanks.